Okay, here we go with this dark energy, this evil dark energy. What is this dark energy that these people talk about? Well, the other day we talked about dark matter, okay, and we found out that the mathematicians, because we're talking about the mathematical physicists, what these people do is they say dark matter is this, and that, okay, and then the next sentence they say, but we don't know what dark matter is. What? Did I hear right? Dark matter is a particle, it's heavy, it's dark, but we don't know what it is. Well, you just told me what it is. Well, what do you mean you don't know what it is? You just told me. And that's the situation, okay? So we have this situation here, okay, where they say, well, look, it's particles, it's ultra heavy, it's dark. Actually, it's not dark, as I showed the other day, or argued the other day, right? Invisible, translucent, or transparent, but not dark. You can see right through it. And you can see the stars and galaxies right through the dark matter halo of any galaxy. So this dark word is wrong. Okay? It's misleading because people say, okay, they're bowling, like the eight bowling ball, or I'm sorry, the eight ball in billiards, or even the bowling ball. The bowling ball is black, dark, right? And is that what this dark matter is? Just a bowling ball? And the answer is no, because if it were black, if it were dark, we would not be able to see through it. And right now we can see through it. Therefore, the word dark is wrong. It should be transparent, translucent, invisible, maybe, any of those words. And so now they're trying to find this stuff. The astronomers are pointing their telescopes. They're trying to see it in the night sky around the galaxies, maybe between the galaxies, right? And the particle mathematicians, the ones who run the accelerators, well, they're smashing protons and who knows what else to see if they can produce this stuff in the lab. Okay, so that's the situation with dark matter. And we had the other day one fellow, his name is Victor Toth, and he talked about this. If you can watch the previous lecture, you'll find that what he had to say essentially about dark matter. And again, a lot of these people are trying to find new equations for this. And here's dark matter. There you see it. Okay, you see the galaxy, and you see the dark matter around it. That's what they're saying that dark matter is. Bunch of particles. You got to think of each one of those particles as very, very heavy. Okay, extremely heavy because they have to produce the mass, the gravitation necessary to prevent first stars from leaving the galaxy, and second, it's got to hold the galaxy together, and then it's the stars on the outside have to travel faster than the ones on the inside. And the only way you're going to do that, according to mathematics, is by putting these heavy particles on the outskirts of the galaxy. And of course, they can't see them, but they say they're there. They've been proven, and so deal with it. Deal with it. You don't like it? Take math. Okay, and this dark matter is also between galaxies. Okay, we find it, that's the theory. Okay, more than a theory, they say they've proven it, now they're looking for it. Okay, but they're saying this dark matter is also between galaxies. And why? Because they believe that galaxies, especially that are relatively close together, influence one another. And they don't see anything in that region, and so they say, well, there's got to be some dark matter, some very heavy stuff to produce what they observe through the scopes. Okay, so that's more or less where all these people stand. Again, dark matter has been proven beyond a shadow of a doubt. You don't like it? Take math. Okay? That's the answer. Okay, the problem here is that you don't find this dark matter between the moon and the Earth. Okay, so here you have the moon and the Earth. You don't find it in between these two objects, because if you were to find it there in between the Earth and the moon, since it weighs so much, right? One little grain of sand of one of these dark matter bits weighs tons, and it would affect the gravity between the Earth and the Moon, or any object. For those of you who believe we went to the Moon, right? Any object that dares go to the Moon, it would change everything, because the gravity would change. So what they're saying is that if we sprinkle dark matter between the Earth and the Moon, both Newton and equation and Einstein's equation, they would both fail. Okay, so you can't sprinkle it here. It's not there. They're not looking for it between the Earth and the Moon. They're looking for this stuff outside of the galaxy. And what they've never justified is, why is this dark matter outside of a galaxy and between galaxies, but not within a galaxy? Why isn't it here between the Earth and the Moon, where we could verify it, right? So yeah, one would think that these people are chasing ghosts. This is what it amounts to. I mean, what else do you call it? The curtain moves, and you say it's a spirit of my grandmother. And you say, hold it, what do you mean the spirit of your grandmother? Maybe it was the air that moved it. But the guy's convinced that it's the spirit of his grandmother, you know? Okay. And this is more or less what dark matter is. You know, it's the spirit of your grandmother out there moving the galaxies around. And why can't we see it? Well, you can't see a spirit, see? It's a soul. It's a concept. Abstraction. Okay, so here we have it. This is dark matter conundrum, again, for you to understand what dark matter really is. And that is that the little yellow thing there at the end of the red line, that's a little star, and you can see that the one above is closer to the center of the galaxy, and the one on the bottom is farther away. And that's going to be the radius there, the r on the denominator. Okay, and so if you raise the little r, if the radius increases, the little v, which is the velocity of the star, should come down. The problem is that when they put their scopes out there in space, in the galaxies, they see the opposite. They see that the stars on the outside are going faster than the ones on the inside. So the farther the radius, the faster it goes. And they say, how can that be if the equation suggests the opposite? If you raise the distance from the center of the galaxy to the star, if that increases, velocity should go down. And so the way they fixed it, they say, oh, we got to fix for it. See, again, they're not doing physics. What they do is just play around with the equations. And they created this variable known as dark matter. And it's mass. That's all it is. And so they put it in the equation and say, okay, that's the only way we can explain it. We've proven it, the existence of dark matter, because it's the only way we can justify that equation. We have to put dark matter in the numerator, quite a bit of it, in fact, all these kilograms that they put in there, right? And yeah, you can't see a kilogram, so I guess that's why dark matter is invisible or translucent or dark or whatever. Yeah, kilograms, it's very hard to see a kilogram. You know, you can see the bag of potatoes, but not the kilograms. Okay, but so they put all these kilograms in the equation. Thanks to that, they are able to mimic with equation. They are able to describe with equation what they observe, what the astronomers observed. And so they said, we've proven it, because what else could it be? Angels, you know? But then they ask everybody to go out and look for it. And they ask astronomers, go look for it. And then they ask the particle mathematicians, go look for it. Okay, everybody's looking for this stuff. What's the problem with this? Well, again, if you can see there the size of those galaxies, and you see the halo around the galaxies, well, it turns out we can see right through them. Okay, that's what happens. You can see right through the halo of the galaxy. So here's the halo, the way they imagine it. So they say, okay, there's dark matter there. Okay, well, if it were dark, it means it would be opaque, and you would not be able to see, you know, the stars in the background. But you do. You see it right through the edges of the galaxy. So again, the question is whether you can talk about dark matter, or, you know, why didn't they call it what they should have called it, transparent matter or translucent matter? Then it would be great. But to say that it's you know, dark just confuses things even further, because everybody thinks that these folks are looking for little pebbles, maybe the size of bowling balls for all we know, that weigh as much as a whole Earth. That's what they're looking for. Very heavy stuff, particles. You can call a bowling ball a particle, but at the universal level, it is a particle, right? And they say all these bowling balls are around the edge of a galaxy, but they're translucent. Yeah. Okay, so what's this got to do with dark energy? Well, if you create the sin, you have to create the, you know, the absolution. You have to absolve the person. Okay, you have to pardon this person. So you have to create this two-world thing. Okay, this duality. And what they did, you know, if you have dark matter, which is something that pulls inwards, it's a gravitational effect that this mass produces. Then you have to explain why the universe is expanding, which is what happened when 1929 you had Hubble. He kind of proved to all the mathematicians out there that the universe was expanding. And later on in, 1998, I think it was, 1998, 99, they went in there and they said, oh, we know what it is. It's this dark energy that's pushing space-time, you know, it's expanding space-time outwards. So you have, on the one hand, dark matter tugging in everything, all matter trying to get together, one with the other, right? All the galaxies trying to get together with each other. But then this dark energy is so overwhelming, it's pushing everything apart. And it's the struggle between good and evil, okay? The good, you can say, is the gravity trying to pull everything together. The evil is trying to separate everyone, make everybody an enemy of everybody else. Kind of like what's happening in the Ukraine. Okay, so where do we start? Well, we have this poor fellow, his name is Feynman, and he was a Nobel Prize winner. And he said, it is important to realize that in physics today, we have no knowledge of what energy is. So they're going to be looking for dark energy, but they don't know what it is. And the question is whether this dark energy thingy is kind of like the dark matter. Like, what is dark matter? Well, it's a particle, it's heavy, it's dark, but we don't know what it is. Okay, and what is energy? Well, it's this dark matter. It's this dark energy. It's particles. It's heavy, and it's dark, but we don't know what it is. Is that the answer going to be here? And you have some people who question whether that is the case. But here you have Mr. Toth, whom we presented last time around, and he said the missing matter is called dark matter, but the remaining stuff with negative pressure. Again, if you have gravity as positive pressure in this case, right? Dark energy is the opposite. It's negative pressure. It's pressure outwards in the universe, right? And you can see dark energy is 73% of all the stuff that fills the universe. Dark matter forms 23%, and all the visible stuff that you see out there is only 4%. Total 4%. That's the calculation. Okay, so he says at the bottom, he says, yet at the same time, we have not the faintest clue as to what these dark thingies really are. And again, I don't understand because they've already defined what it is. They're saying it's little balls that weigh a lot, particles, right, that weigh a lot, and they're dark. So we know what it is. It's particles that weigh a lot that are dark. That's what it is. We're done. It's like, what is a dog? Well, a dog has two ears, 2 eyes, a tail, a body, but I don't know what a dog is. I thought you just described the dog. I don't know what a dog is. Okay, so here we have the Big Bang. So this is where we start. We had the Big Bang, and everything is pushing outwards from the moment of the Big Bang. Okay, you can see here. Here's the original explosion. Okay, that's the Big Bang. Frame number 2, because they never start frame number 1, and everything is pushing outwards and creates this glass that's tilted. All the beer came out of it. Okay, so this is where it starts, and what they're saying is what's pushing all this matter outwards is dark energy. Inwards is what dark matter tries to do, but dark energy is more powerful, and it's just pushing the entire universe, this universe outwards. Okay, and when they do that, they run into this balloon analogy, and here it is. Okay, and what they do is they have this thing, which is the explosion of space-time that you just saw, and it starts from nothing, from a little point, okay, which you'll see here, okay, and it just expands. And what's expanding all that is known as dark energy. What's trying to pull all these galaxies together, the yellow dots there, is dark matter. But whatever dark energy is, it's winning the battle, and it's pushing the whole universe outwards. Okay, and this is what they talk about. The question is, what's the white stuff? What is it pushing out against? And that's a question you'll never have an answer to, and in fact they say it's unscientific because we cannot imagine what's out there. But it turns out that's what destroys their theory, because if you cannot tell me what the white stuff is, you don't even have a physical interpretation. You cannot tell me what you're talking about. You have to identify the white stuff. You got to tell me what that white stuff is, because if the balloon is expanding, why does a balloon stop there? What continues? That's what you got to answer. If you can't answer that, thought, I mean, you can say it's thought, if you cannot answer that question, you cannot even begin your presentation. You don't have a theory. Okay, a theory is what? An explanation. Okay, so they don't have an explanation for this balloon analogy. That ridiculous, really, because they think that the universe is this sphere and the galaxies are not really inside. What they are is on the outside, just on the surface of this expanding balloon. Okay, so all the galaxies are on the surface of the balloon, like if you see a balloon that's polka dotted, and you blow the balloon and all the little dots become bigger, but they also become separated from each other because the balloon is stretching, right? And so one of the questions that has always come up is, why don't the galaxies also get bigger and bigger and fly apart, kind of, as the balloon expands? And they say, well, locally, both gravitation and electromagnetism pull everything together. And then galaxies can separate from each other as the balloon expands. Okay, and then why does the Andromeda galaxy, why is it blue shifted? Why is it coming towards us and will apparently hit the Earth around 2.2 million light years in the future? 2.2 million years in the future, because, it's, I guess, traveling at the speed of light. And so Andromeda is coming towards the Milky Way, and so is the rest of the local group. It's like they're all coming slowly together. And you're saying, well, hold it, if the balloon is expanding and all these galaxies are on the surface, should these galaxies have more distance between them as time goes by? That's not the case with a local group. The local group is coming together, and the answer to that is, well, here, gravity is stronger than dark energy. The dark energy is not powerful enough to overcome the attraction, the gravitational attraction between galaxies. That's the answer. Okay, so it's all ad hoc. Okay, they're trying to explain why when they look through the scope, they see what they see, and then they try to explain it, usually with equations, with mass, with gravity, and that's the science we have today, the mathematics that we have today. Okay, so there are some skeptics of dark matter, dark energy. I think, I don't want to put words in his mouth, but I think Mr. Toth, whom I talked about the other day, is an atheist or becoming an atheist or at least an agnostic in dark matter and dark energy. So dark energy could be just an artifact of the so-called cosmological constant. You know, Einstein's cosmological constant, his biggest error, as he said, or the potential energy of a so-called scalar field, okay? Or maybe just energy of the quantum vacuum. Quantum vacuum. What is the quantum vacuum? All these particles that come in from the void, you know, they make the void, and one comes in, well, both of them come in, they separate, and they live momentarily. It's called a virtual particle. Then they go back, forming part of the vacuum. And the question is, when they come out, do they leave a hole behind momentarily? Is there a hole in space? And what is that hole in space? If space is made out of particles, what's the hole? The hole in what? So this is the issue. You know, they never were able to figure all these things out. Okay, they just talk about the particles coming out, doing this, and putting it back because they need that to explain what happens in the lab. That's their explanation. But then they don't take that extra step and say, well, when these two particles came out of being part of the vacuum, what was left behind? A hole in the vacuum, a hole in nothing. It's scary stuff, really. You wonder how much beer these people drink, you know. Anyways, so he says, I believe that we need to find ways to, you know, actually detect these dark thingies before we can say anything definite about their nature. Perhaps these dark thingies do not even exist. Ooh. Blasphemy, blasphemy, because it's already been proven. And this gentleman, who is not officially a physicist, he says he's a part-time physicist, meaning that he's a self-taught physicist, mathemagician really, and he's suggesting something that goes counter to the catechism of the establishment, you know, the party line, and that is that they've already proven that dark matter and dark energy exist, and he's questioning that. Okay, they are mirages of sorts because we are doing what? The math using the wrong theory of gravity. What he's working on is essentially a modified, called MOG, M-O-G. It's a modified gravity. That's what he's working at. He wants to modify the equation. He's saying out there at that distance, dark matter and dark energy do not really exist. What we have is simply a different equation should be used to mimic or describe what's happening at, you know, at places like the edges of the galaxy or between galaxies. Okay, so they're looking at the equations. They're saying there is no real dark matter, dark energy. At least that's what they insinuate. Okay, that's their gut feeling, that there really isn't any dark matter, but they can't go out there and say it. Because if they do, they're going to be, you know, be ostracized. They're going to be kicked out of the club. And so they have to be careful what they say. And the worst thing they can say to a fellow like Toth is, you're not a physicist anyways. You don't understand. That's, he'd die if they tell him that, okay? Okay, here we have another lady, Sabine Hassenfelder, and she says, the low redshift supernovae were in one direction, while the high redshift ones were in another direction. Problem, it's a skewed sample. She was talking about, you know, these papers that analyze the fact that maybe, just maybe, dark energy doesn't exist. And again, she's in dark matter, just in case also, she has a little doubts, I think more than doubts, on dark matter. Again, she's playing around with the equations. Okay, so all these people are playing with the equations, and they're not looking through the telescope saying, I'm not going to see this stuff, so why bother? What I'm going to do is just do my calculations and try to mimic with the equation what these people are observing out there. And so it says, a recent paper claims dark energy does not exist. Talk about blasphemy. You know, she could get in trouble for this, you know. If dark energy is real, the universe will expand faster and faster until all eternity. Okay? All this stuff pushing all the stars, everything outwards, right? If there's no dark energy, the expansion will slow down instead, and it might even reverse. In other words, dark matter triumphs over dark energy, so to speak. Okay? In which case, the universe will collapse back to a point. Okay, so apparently this lady, she believes that we came out of a point, and we probably go back to a point known as the oscillating universe. You know, we started out at a big bang, get to the big crunch, or maybe not even reach there. You know, somehow gravity pulls everything together again, and we go back to the point. And it's this point to expansion, back, point to expansion, back, and so on. So this is the oscillating universe. I guess she's thinking about, and she's trying to, describe that with an equation, that process, okay, of why matter comes back together to be a point. Okay, and here's the paper she's referring to. The fellow said, the best fit to data rejecting isotropy and consistent with no acceleration. So he was saying there is no acceleration of galaxies outwards from each other. There is no dark energy, essentially, pushing all these galaxies outwards. Okay, thus the cosmic acceleration deduced from supernovae may be an artifact of our being non-Copernican observers, rather than evidence for a dominant component of dark energy in the universe. So some people are starting to question, this came out 2019, by the way, so some people are starting to question, from the establishment, whether there is such a thing as dark energy out there. Is there something pushing all these galaxies outwards? Or was it simply from the initial Big Bang explosion, whatever that was, So we have this explosion, and it's like a hand grenade. You don't really need something pushing the little shrapnel, on and on and on. It's from the initial explosion that, you got everything going outwards, so to speak, But, even when you throw a hand grenade, the pieces don't come back together. But you say, well, there's not enough matter to produce this gravitational pull, okay? But that's what these people are looking at. They're saying, okay, there was this explosion, but now gravity is going to pull everything back together. And so that's what they work on. They work on the equations. They're simply trying to mimic with their equations, again, tautology, right? They're trying to make ad hoc equations that match what they observe out there. That's all that mathematical physics is. Do they have a mechanism? I mean, what is the mechanism? I'll concede dark matter. Let's start there. I'll concede dark matter. Bunch of particles, heavy particles, whatever. Okay, so you have all these loose, discrete particles all around the galaxy. What is the mechanism? By what mechanism do they compel stars to go faster? And by what mechanism do they prevent stars from leaving the galaxy? I mean, if they can't answer that, they don't have physics. What they have is just an equation that says, this is the description. And that's where we stand today, okay? Okay, so here we have something we discussed the other day, and I was supposed to put this as the question and answer segment, but it's part of this subject, so I'm just going to introduce it here in what I've been covering right now. And it's got to do with this. I showed this the other day, that under the rope model, you have this linear regime, which is between any two stars. And on the right, we're going to have the sun, and on the left, we're going to have the Centauri system. And I'm saying that any object that tries to leave the solar system will encounter the bird's beak, which is a region that has no gravity. Okay, I call it the linear regime. Okay, and so here it is. You can see it again. You can see the sun on the right, the Alpha Centauri on the left. Okay, Proxima Centauri, whatever. And any rocket or whatever that tries to leave the solar system will encounter this region, this linear regime. Okay, that's at the end of the bird's beak, and this is how you would be traveling for eons through these ropes that come into each one of the atoms of your spaceship and you yourself. Okay. Why am I putting this up there? Well, I'll tell you why. Because a fellow asked the question. He says the following: because I don't quite get how the lack of gravity in the linear regime slows down the spaceship when in fact there's less fan out of ropes on it from either side. Yeah, I guess he has problems visualizing this. He's saying, look, the farther you get away from the sun, the fewer ropes you have, right? Because the ropes are coming together the farther you are. And he says, we should be traveling, if anything, faster and not slower. Right now we have the pioneers, that's what this was all about. The pioneers are closer to the sun than they should have been. They should have been farther out. Okay, and so he's saying, how do you do it with ropes? I don't understand. Looks like that, and the farther you go out there, the ropes come in and they become a single coaxial. You should be traveling faster rather than being pulled towards the sun. That's what he's questioning here, okay? My understanding of it is that considering the so-called mass weight of the spaceship relative to either star and the distance remains the same, the factor that might be changing is g, the gravitational constant g. The gravitation, oh, okay, there is the gravitational constant. It might be not be a constant after all, okay? You should research that and do your calculations. I did quite a few of those on the gravitational constant. Now it's your turn. Okay, is that what Bill is saying here when he states that Newtonian gravity is no longer at play here? Okay, and before I answer this gentleman, there's another gentleman who put a note. He says, so the ropes don't follow a straight path between objects? Why not? And I'm assuming, I don't want to put words in his mouth, but I'm assuming he's referring to the bird's beak. You can see there's a curve there. And so he thinks that the ropes there are curving. Okay? I think that's what he's referring to. He's saying, I thought they were all straight, they were all tight. And the answer is yes, they are all tight. And so let's answer this gentleman first. Okay, then move on to the first one. Here it is. We can produce these patterns all with straight lines. And you can see they're curved. You say, how can it be curved? It's curved, but it's all done with straight lines. Okay, so all these two patterns were made with straight lines. And that's essentially what we're saying that happens in the bird's beak. We're doing it all with straight lines. In other words, we're doing it all with taut ropes connecting atom to atom. Okay, we're going to be producing a curve. Okay, a curve of the net, you can say, of ropes. We're going to produce a curve of the net through with straight lines. Okay, and so here, let me show you the bird's beak. Okay, this is the bird's beak, and I did this all with straight lines. Okay, all this is done with straight lines, but you can see a curvature at the top. And why is this curvature? Well, this curvature, we have to understand why, the cause, what triggers this. It's that if I ask you how many atoms are there at the top, at the pole of the sun, versus how many are in its equator in this picture. Well, you would say there are more atoms around the belly, the center of the sun, than they are at the very North Pole. In fact, at the very North Pole of the very South Pole, there should be a single atom that's out there, you know? And so there should be only a single rope from that atom to anything like to the Centauri system. On the other hand, if you look at all the atoms that are in the middle of the sun, there should be gazillions of them there. And so that's why you see more ropes running down the center, okay, what's going to become the linear regime, than you have at the top. Okay, so all ropes are connected from one sun to another, like from our sun to the Centauri system. So I put those ropes there, I drew those. But the reason you get that curvature is that as you go down this object, the sun, you should get more and more ropes as you get to the center of the sun. Okay, so that's what produces the bird's beak. And the bird's beak, as you can see, is not a perfect square of the distance function like is Newton's. Newton's would be a perfect triangle. In fact, I should have drawn that there. But Newton would be a perfect triangle. This is not a perfect triangle. This is a curved side triangle. Okay, it's not an exact triangle. Okay, so that's the situation there. Okay, so where do we go from here? Well, here you see the linear regime. Okay. And I've drawn the bird's beak on both our sun, which is the one on the guy on the right, I should have labeled that, and the one on the left is the Centauri system, Alpha Centauri or Beta, whichever, doesn't matter. So the issue is you can see the bird's beak there, okay? Why? Because again, most of the atoms are in the center of the sun and of the Alpha Centauri there, and relatively fewer, much fewer, are in the ones that go straight ahead from sun to sun. Okay, so you should produce a bird's beak under the rope model, under the rope assumption. Okay, okay, so here you have our starship, and it's going to leave the Earth. Okay, and so it travels, and when it's close to the sun, it's more or less square of the distance. So the rope model pretty much matches Newton, the point at A there. Okay, that's our rocket there at A, and the rope model essentially mimics or matches almost perfectly Newton's square of the distance function. No problem. But what happens when your spaceship hits the point where more and more the ropes go straight ahead from our sun directly to Alpha Centauri system? What you have is that linear regime. And there is no gravity because you don't have the square of the distance gravity in that region. And so what happens when your ship comes out of the sun, yeah, in this case out of the solar system, once it hits that region, let's assume it was just a fixed place. It's actually a gradient, okay? It's a nuanced region, you could say. But let's assume that there's a clear-cut place. At that point where you hit the linear regime, well, what's going to happen, it's like if your rocket hit a brick wall, okay? And I liken it to a diver going from water to molasses, assuming it's that clear cut. It's not, but this is just for illustration. If you go from water to molasses, you're going to be slowed down. And that's essentially what's happening. You can also look at the spaceship coming backwards from Alpha Centauri to the sun. You might expect, if you use the square of the distance, you might expect the rocket at sea, okay, assuming it's turned around facing the sun, it's going towards the sun, you might expect the rocket at sea saying, okay, I should expect, according to Newtonian square of the distance, I should expect being drawn to the sun here. And it turns out you're not drawn to the sun because it turns out that, you got to go further down if you want to have gravity. You're not yet in the square of the distance gravity regime. And so this is what's happening here. What's happening is that what we're doing here is comparing Newton against the rope. In other words, how did these people calculate that the pioneers were not where they were supposed to? Well, they used Newtonian gravity. That's how they figured all this out. Okay, so let's understand the issue. The issue is that NASA, when they figured out that the pioneers were not as far out as they should be, they used Newton, and they used the square of the distance equation. But it turns out that the probes were closer to the sun. And the issue there is, again, it's like the rocket hit a brick wall, so to speak. It's nuanced. It's very gradual. In fact, that's what they measured, that it kept losing speed as it went along. Okay, so that's what you got to mimic with the equations. What they did was they went with the equations. They also said, oh, there was a heat dissipation there, and preferentially in the direction of travel, and that's what slowed it down. That was their argument. And I'm saying, no, what you have is this probe is moving into a region that is not quite Newtonian. Okay, it's not Newtonian. It's already changed, and there is no gravity in that linear region. So it's like if it hit a brick wall, it slows down. It's starting to slow down as it tries to move out of the solar system. And again, we're comparing the rope model versus the square of the distance model. Okay, so that's what we're doing. So don't think of it in terms of ropes. Are there more ropes, less ropes? What you got to compare is against Newton, because that's how they determine that they're slowing down or decelerating towards the sun. Okay, so that's the story. Essentially, the probes, Pioneer 10 and 11, they hit this region where there is no gravity. And so now instead of thinking in terms of Newtonian gravity, you got to think of a no gravity region, or fewer, actually it's less and less and less, but we're just going to talk about the extremes and say a no gravity region. And so now this thing is drifting, and you're expecting it to be farther out because of Newtonian calculations, and it's not there because it doesn't encounter gravity, or it encounters really less gravity as it goes, as it leaves the solar system.